In an earlier video, we saw how Pythagoras' theorem could be applied to find the distance between 2 points in 2D space. But what about 2 points in 3D space? Well, that's what we're going to look at in this video. I think it goes without saying that finding the distance between 2 points in 3D space is incredibly useful. And not only is it used for its most obvious application, for finding distances between locations in 3D space, it's also frequently applied in vector mathematics. So this is really another one of those must-know topics. So let's first look at our 2D example again. Given 2 points in 2D space, so let's draw some very rough axes. So this would be our x, this is our origin, this is our y. So given 2 points in this 2D space, we found the distance between those points by calculating the length of the hypotenuse of a right-angled triangle that was constructed using these points. So the hypotenuse is the line that runs between the points, and we wanted to find the length of that edge of the triangle in order to find the distance between the points. We also created an edge that ran parallel to the x-axis and an edge that ran parallel to the y-axis. And because these edges run parallel to the x and y-axis, we know that indeed they meet at a right angle, and that means that we know, because it's a right angled triangle, we could label this A, label this B, label this C, and Pythagoras' theorem tells us that a squared plus b squared equals c squared, which allowed us to rewrite this as c is equal to the root of a squared plus b squared. Now, given the coordinates of these 2 points, we saw how easy it is to work out the length of A and B, because A is only travelling in the x-axis, which means that because this edge is parallel to x, we can simply take the difference of the 2 x-coordinates of the point to find the length of this edge. Likewise, B is only travelling in the y-axis because it's parallel to y. We can take the y-coordinates of these points, find the difference between them, and that gives us the length of B. So that was our 2D example, but how does this extend into 3 dimensions? Well, allow me to scroll down a bit and allow me to draw a set of 3D Cartesian axes. So I'm going to have a line like so, and then I guess a line that comes out like so, and another line like this. So this is going to be my y-axis, which we know is perpendicular at a right angle to the x-axis, which is all perpendicular to our z-axis. So this is a 3D set of Cartesian axes, and we're going to create 2 points in this 3D space. I'm going to create a point down here, and let's create a point over here, and this is going to be the point x1, y1, z1, and this is going to be the point x2, y2, z2. Now, in 2D space, we constructed a right-angled triangle between these 2 points, such that the hypotenuse was the edge that ran between the points in order to calculate the length of the hypotenuse. Well, we can do the exact same thing in 3D. We can construct a right-angled triangle in 3D space, such that the hypotenuse is the edge that runs between the points, and if we can somehow then apply Pythagoras to that triangle, we'll be able to find the length of the hypotenuse and thus be able to find the distance between the 2 points. So we can create our hypotenuse. We know that's the edge that runs between the 2 points, but these points are in 3D, not in 2D. So how are we going to go about creating the other 2 edges? Well, what I'm going to do, I'm going to create one edge that runs parallel to the y-axis, and because it's going to run parallel to the y-axis, it allows us to use the coordinates of the point to work out the length of that edge. So let's think about how we're going to create an edge that runs parallel to the y-axis. So it's going to be this edge, it's going to run straight down. And how do I know how long this edge is going to be? Well, if it's only moving in y, that means its start point is going to be x2, y2, z2. Its end point can't change in x, and it can't change in z. So its end point must be x2 and z2 in x and z, but in y, we want to go all the way down to where our first point is. So in y, we're going to go down to y1. So we're going to have a point floating down here somewhere, and it's going to allow us to create an edge that is parallel to our y-axis. It's traveling just in y. And because it's traveling just in y, that allows us to know that the length of this edge is going to be y2 minus y1. Because we're only traveling in y, the length of the edge is the difference between the y coordinates of those 2 points. So that's one of the edges. The third edge of our right-angled triangle is going to connect these 2 points. And how do we know that this forms a right-angled triangle? We'll look at our start point, x1, y1, z1, and look at our end point, x2, y1, z2. We're not moving in y, we're only moving in x and z. So if we're only moving in x and z on this edge, and we're only moving in y on this edge, and as we've seen, the y-axis is at a right angle to the z-axis, and it's at a right angle to the x-axis, which means it is perpendicular, it's at a right angle to any line that lies on the xz plane. So because this line lies on the xz plane, and because this line only travels in y, we know that they're at a right angle to one another. So we're trying to find the distance between the 2 points. We're trying to find this edge here, which I'm going to name D. We know how to calculate the length of this edge using our y coordinates, but we still need to find the length of this base edge in order to use Pythagoras' theorem to calculate D. So how are we going to get the length of this edge? Well, it's travelling in x and it's travelling in z, we know that, but it's not travelling in y. So what we have is some edge that's travelling in some arbitrary direction on the xz plane. Well, the xz plane is 2D. So we've seen how to calculate the length of a line in 2D. We saw that just up here. If we have some edge travelling in 2D, if we imagined instead of this being the xy plane, it was the xz plane, we've seen if we have an edge travelling in 2D, how we can use Pythagoras to calculate that. So what we can do is construct another right-angled triangle. And in this case, the right-angled triangle is going to have one edge that runs parallel to the x-axis, something like this, another edge that runs parallel to the z-axis. Because they're running parallel to 2 axes that we know are at a right angle to each other, it forms a right-angled triangle. We could call this edge A, this edge B. This is our hypotenuse. And if we can work out the length of our hypotenuse, we can then use that and this edge to calculate D. So let's look at our triangle that's lying on the 2D plane first. So what do we know from Pythagoras? We know that a squared plus b squared is equal to h squared. And we know here that a is travelling parallel to the x-axis. That means it's only going to be moving in x, which means we can find the length by taking the difference of our 2 x coordinates. So a is going to be x2 minus x1, and we need to square that. B is travelling parallel to our z-axis, which means that we're only travelling in z, which means we can take the difference of our 2 z coordinates to find the length of B. So z2, excuse me as I erase that and rewrite that so it's more clear. So z2 minus z1 all squared is equal to h squared. And we know from that that we could go ahead and find the length of h as the square root of x2 minus x1 squared plus z2 minus z1 squared. Now, as we're going to see in a second, we actually don't need to take the square root of h. We're just going to need the value of h squared. But for now, here we have h. So we know the length of h. We know the length of this edge. It's y2 minus y1. And so we can now use Pythagoras on this right-angled triangle to work out the length of D. So let's scroll down just a bit. We know that D is going to be equal to, or let's just write this as d squared to begin with, is going to be equal to h squared plus y2 minus y1 squared. So y2 minus y1, all of that squared. And what is h squared? H squared is this, x2 minus x1 squared plus z2 minus z1 squared. So d squared is equal to x2 minus x1 squared plus z2 minus z1 squared plus y2 minus y1 squared. Let's rewrite this for clarity and so that it's easier to remember. So d squared is equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That means that d, therefore, is equal to the square root of all of that. So x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So this is the distance between 2 points in 3D space. So let's compare that to our 2D version. So this is our 3D version. We're dealing with an x, y and z coordinate. Well, our 2D version, if we remember, was d is equal to, and I guess I'm gonna refer to this as d subscript 3, so we know it's 3D, and d subscript 2. That's just my notation so that we can remember that this is indeed 2D and not equal to the one above. So this is in 2D. It's equal to x2 minus x1 squared plus y2 minus y1 squared. So we can actually see that it's actually not that much more complicated when we move into 3D. We're simply adding in a term underneath our square root that takes into account our z axis. So this is our 2D version. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And this is our 3D version. D is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Incredibly easy to remember and incredibly useful to us. So let's now use this formula, this 3D formula, to find the distance between 2 points in 3D space. So I'm going to bring up a new whiteboard and hide out everything else. Fantastic. And let's find the distance between the point 2, 3, 4 and the point 8, 1, 6. And again, our formula for doing that is that d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Now, just as in our 2D version, it doesn't matter which point is going to be x1, y1, z1, and which point is going to be x2, y2, z2, because no matter which way we subtract the points from each other, whether we get a positive distance or a negative distance for the edge in x, y, and z, because we square those values, we're always going to get the same values here, which means that distance is always going to be evaluated in the same way. So I'm just, for an arbitrary choice, going to take 2, 3, 4 as x1, y1, z1. So that means that d is equal to the square root of x2 is 8, minus x1 is 2, squared, plus y2 is 1, minus y1 is 3, squared, plus z2 is 6, minus z1 is 4, squared. So if we now work this out, d is equal to 8 minus 2 is 6, so 6 squared, plus 1 minus 3 is minus 2, so minus 2 squared, plus 6 minus 4 is 2, so 2 squared. Let's scroll down to give ourselves some more room. That means that d is going to be equal to the square root of 36, minus 2 squared is 4, and 2 squared is 4. So it's equal to the square root of 36 plus 4, which means that d is equal to the root of 44. Now, this isn't a nice round number, so I'm going to leave it written as the root of 44. And it really is that simple. We can just plug numbers into that formula. It is a distance formula, only it's this time this is the distance formula in 3D. We can simply take the coordinates of 2 points, plug them into that formula, and very quickly get the distance between those 2 points. So now that we've seen an example, I'd like you to answer some questions on your own. So I'm going to bring a new whiteboard up. In actual fact, we've got room for the first question down here, so let's scroll down. And the first question I'm going to set, I would like you, using that distance formula, to find the distance between the points 6, 3, 1, and 4, 6, 9. So go ahead and use that formula, find the distance between the points. If you get stuck or once you've found the answer, unpause the video because I'm going to work through the solution. Okay, welcome back everyone. So we're going to be using our distance formula. By now we should be very familiar that that is the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Again, it doesn't matter which point is x1, y1, z1. I'm going to take this first point here as x1, y1, z1, and I'm going to plug the numbers into our formula. So the distance is equal to the square root of x2 is 4, minus x1 is 6 squared, plus y2 is 6, minus y1 is 3, squared, plus z2 is 9, minus z1 is 1, squared. So as we work that out, d is going to be equal to the square root of 4 minus 6 is minus 2, squared, plus 6 minus 3 is 3, squared, plus 9 minus 1 is 8, squared. So d is going to be equal to the square root of 4 plus 9 plus 64, which means that d is going to be equal to the square root of 77. Now that's not a round number. I'm going to personally leave it as root 77, but in case some of you used a calculator to work this out rather than working on paper, that is approximately equal to 8.775. So if you got either of these answers, either root 77 left in this form, or an answer that's approximately 8.775, then you did indeed get the correct answer. If you didn't get the correct answer, check that you fully understood how we can apply this formula to these numbers. So either maybe perhaps you didn't quite remember the formula correctly, or maybe when you worked the formula out you made a slight error with the numerical calculations, which is very common. I'm always making slight errors when adding and subtracting numbers and making sure that I'm squaring numbers correctly and things, so it is very common. Just double check, see how I've worked through this, make sure that you've done the same, and hopefully you can see if you did make a mistake where you went wrong. So that's our first question. I'm going to set 2 more questions in this video. The first question, well, the next question, second question, which I'm going to do on a new whiteboard, is again to find the distance between 2 points, and this time the points are 5, 2, 4, and the second point is 15 in x, 8 in y, and 16 in z. So go ahead and find the distance between those points. Pause the video whilst you're doing that, and when you come back I'm going to work through the solution. Okay, welcome back everyone. So we know our distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Let's just plug our numbers in again. Doesn't matter which point is x1, y1, z1. I'm just going to grab this guy because he's here on our left first. So let's plug our numbers in. So d is equal to the square root of x2 is 15 minus x1 is 5 squared plus y2 is 8 minus y1 is 2 squared plus z2 is 16 minus z1 is 4 squared. So carrying this on, that means that d is equal to the square root of 15 minus 5 is 10 squared plus 8 minus 2 is 6 squared plus 16 minus 4 is 12 squared. That means that d is equal to the square root of 10 squared is 100, plus 6 squared is 36, plus 12 squared is 144, which means that d is equal to, well, 100 plus 36 plus 144 is going to give us 280. So d is equal to the square root of 280. Again, it's not a round number, so maybe you've left it in this form if you were working on paper, but in case some of you used a calculator to solve, this is approximately equal to, as I give myself some room to write this down, so that is approximately equal to 16.733. So either way, this is the answer you were looking for the distance between those points. So here's one final question. I'm going to set this on a new whiteboard just to ensure that we have enough room for it. So this question is going to be slightly different. I'm going to tell you that the distance between 2 points is 20 units and that the coordinates of the point, the first point, is 5 in x, 6 in y, and 10 in z, and the coordinate of the second point is 9 in x, 1 in y, and z2 in z. So what I'd like you to do is, knowing that the distance between these 2 points is 20, I'd like you to find the two possible values of z2 that will give us a distance of 20 between these 2 points. So go ahead and pause the video, and when we come back I will work through the solution. And just worth mentioning, you do have everything you need to work this out. Even if it's slightly trickier and requires a bit of thinking, you do actually have absolutely everything you need to work out this answer. So go ahead and pause the video and we'll be right back. Okay, welcome back everyone. So hopefully you were able to solve this problem. So let's start out. What do we know? Well, we know that that distance formula is going to relate these three pieces of information. So that means, let's start out by writing that d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Now in this case I know the value of d, the value of x2, x1, y2, y1, z1, so the only variable I don't know is z2. So what we need to do to solve for z2 is rearrange this equation. So the first thing, if I'm trying to get z2 on its own, I need to get rid of this overall square root. I can do that by squaring d. So d squared is equal to x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. I can then subtract both x2 minus x1 squared and y2 minus y1 squared from both sides, leaving just z2 minus z1 squared over here on the right. So d squared is equal to, oh, my apologies, I need to make sure I subtract that from both sides. So d squared minus x2 minus x1 squared minus y2 minus y1 squared is equal to z2 minus z1 squared. How are we going to get z2 on its own? Well, the next thing I want to do is cancel this square root. That means I need to take the square root of this entire side. So that means the square root of d squared minus x2 minus x1 squared minus y2 minus y1 squared is equal to z2 minus z1. So we're almost there. I want to get z2 on its own. I'm going to add z1 to both sides to cancel this subtract z1. And just so that it's written a little more clearly, when I write add z1 on the left hand side, I'm going to put z1 plus and then the rest of this. That to me is a little more clear. So z1 plus the square root of d squared minus x2 minus x1 squared minus y2 minus y1 squared, and that is equal to z2. So you may be asking yourself, well, how can we get two answers from this? Well, you need to remember that when we're dealing with the square root in the distance formula, we're dealing with a distance that's going to be positive, which means we only ever take the positive square root. But here, with this root, we're not dealing with a distance. We're trying to find a coordinate. So we must remember that this is plus or minus the square root of d squared minus x2 minus x1 squared minus y2 minus y1 squared. Because of that, there are two possible values for z2. The first is going to be z1 plus the root of all of this. The other is going to be z1 minus the root of all of this. So let's work out those two possible values for z2. So z2 is going to be equal to, and we can plug our numbers in now as we start working this out. So we know that z1, and I'm going to actually rewrite these coordinates down here as we start plugging numbers in. So let me erase this. I'm going to rewrite our values into this. So we know that x1, y1, z1 is the point 5, 6, 10, and that x2 is 9, y2 is 1, and of course we were trying to find z2. So now that we've got that, we can put these numbers into the equation. So I'm just going to write z2 on the left is equal to all of this on the right and start putting numbers in. So it's equal to z1 plus or minus the square root of d squared. We saw that d was equal to 20 earlier, so d squared, 20 squared, minus x2 is 9, minus x1 is 5 squared, minus y2 is 1, so 1, minus y1 is 6 squared. So that means z2 is equal to 10 plus or minus the square root of 20 squared is, well, I'm going to leave that in that form for now, minus 9 minus 5 is 4, so minus 4 squared. 1 minus 6 is a negative 5, so minus 5 squared. Now this is going to be really important when we come to evaluate this, that you make sure to remember the order of operations. So when I get to that, I will mention exactly what I mean by that. So z2 is equal to 10 plus or minus the square root. 20 squared is 400, minus 4 squared is 16. Now here you may think, well, we've got a minus and a minus. Does this not become plus 5 squared? But remember, we take 1 minus 6 because it's in parentheses. We evaluate that first. That gives us minus 5. The next thing we need to evaluate after parentheses is our exponent. So we need to take the square root of minus 5, which gives us a positive 25, before we then subtract it. So we are still subtracting 25, not adding, because the square takes precedence before this subtraction. So z2 is equal to 10 plus or minus the square root of 400 minus 16 minus 25. That means z2 is equal to 10 plus or minus the square root of 359. So there are two ways now that you could give me the two coordinates for z2. You could leave it in this form, or you could write it as z2 is equal to 10 plus root 59, or 10 minus root 359. So you could have said these are the answers for z2, and I would accept that. That is mathematically accurate. Or we could go through and use a calculator to work out the values. I'm going to do that. I'm going to use a calculator to work out the value of root 359. So root 359 is approximately equal to 18.947. So because it's approximately equal to that, that means that z2 is equal to 10 plus 18.947 approximately, but I'm just going to say equals from here on out. Or z2 is equal to 10 minus 18.947. That means that z2 is equal to 28.947 or it's equal to minus 8.947. But why did I want to work these out as numerical values? Well, I want to prove to you that everything we've just done in this question does indeed satisfy the fact that the distance is 20. We know it should. We've rearranged the equation. Everything should work. But what I'm going to do is I'm going to take those two values of z2 and plug them back into this coordinate. That gives us two possible coordinates here. And we're going to put each of those through our distance equation to make sure that the distance comes out. It's not going to be exactly 20 because we have rounded the value of root 359, but it's going to be close enough that we can see, yes, this is accurate, this is the correct working. So what I need to do that really is a new whiteboard layer. So I'm going to bring up a new layer, and let us just remember what we were trying to prove. So we're trying to prove the distance is 20, and we're trying to prove that with our first point being 5, 6, 10, and our second point being 9, 1, z2, where z2 was equal to either 28.947 or minus 8.947. So let's take the 28.947 first. We'll plug that in for z2 and we'll evaluate our distance formula. So distance is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. Let's plug numbers in. So d is equal to the square root of x2 is 9 minus x1 is 5 squared plus y2 is 1 minus y1 is 6 squared plus z2 is our 28.947 minus z1 is 10 squared. We can now evaluate this. So d is equal to the square root of 9 minus 5 is 4, so 4 squared. 1 minus 6 is minus 5, so plus minus 5 squared. 28.947 minus 10 is 18.947 squared. That means that d is equal to the square root of 16 plus 25 plus, and I am going to use a calculator to work this out, this is 358.98889 or thereabouts. So we can add all those together, and that should give us that d is equal to the square root of 16 plus 25 is 41, plus 358 point blah 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 is 399.98889. If we use a calculator to work that out, it means that d is equal to 19.9997, which is approximately equal to 20. Where's this difference come in? Again, this difference comes from the fact that we approximated the square root of 359 when we generated these values. Therefore, the values for the z2 aren't perfectly accurate, and therefore when we plug them in, that rounding error results in a slightly inaccurate distance. So we've proved that our first point, our first coordinate, 28.947 works. Let's now go through and prove that our second coordinate works. So d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. That means that d is equal to the square root of x2 is 9 minus x1 is 5 squared plus y2 is 1 minus y1 is 6 squared plus our new z2, if you recall, is minus 8.947. So minus 8.947 minus 10 squared. Well, d is going to be equal to, again, 9 minus 5 is 4, so 4 squared, plus, again, 1 minus 6 is minus 5 squared, plus minus 8.947 minus 10 is minus 18.947 squared. Now, hopefully, those of you that are paying attention will see we are indeed going to get the same value because we have 4 squared plus negative 5 squared. Well, we had that before. We had plus 18.947 squared, and now we've got plus negative 18.947 squared, but we know those two values are the same. Now I am going to work this out just one step further to prove that we are going to get the same value. So we know that this is equal to the square root of 16 plus 25 plus, if you evaluated the square of negative 18.947, you would get 358.9, there's a point, 0.98809. So remember, d is equal to the root of 16 plus 25 plus 358 point some stuff. D is equal to 16 plus 25 plus 358 and some stuff. So that means that we are, when we evaluate this, going to get the exact same answer as before, thus proving that both of the coordinates we calculated with our rearranged equation, both of those are valid coordinates, the only valid coordinates that would give us a distance of 20 units between those 2 points. So to recap, we saw in this video how we can take Pythagoras' theorem in 2D, and we saw how we could use that to derive the distance between 2 points in 3D space. So here was our 2D theorem, and we used that to derive a 3D theorem. And we also saw, in addition to finding the distance, it actually allows us simply to define a relationship between 2 3D points, their coordinates, and the distance, which can allow us to solve problems other than just simply finding the distance. In that last question, it allowed us to find 2 possible coordinate values that would satisfy that distance. So hopefully you can see just a little bit of the power and the use of this new 3D distance formula. It is incredibly important to us in computer graphics. And with that, that is going to wrap up this video. Thanks a lot, everyone.